So, but I don't hear any interference, and it certainly is better than all the static I was experiencing there.
Okay, good.
All right, so what are we doing this year? Are we in trig or anything?
Yeah, so last semester was more pre-calc algebra review, and then this semester we're starting up with trigonometry.
Okay. All right.
So we started the unit circle and radians and degree conversion, and then the 6 trig functions.
Perfect. I have the perfect session for you.
Okay.
First of all, without a calculator, can you tell me what that is? And if you can't, that's fine. I know what to do if you can't.
I know the exact value.
Without a calculator, can you give me the radical value?
No.
All right. Let's go through the unit circle then. Now, trig is a lot more memorizing than precalculus. There really is quite a bit of memorization for trig. And it all starts from stuff I'm writing on my screen. Do you know the dimensions of these two triangles? This is a 45-45. Triangle on the left. Opposite the smallest angle is 1. Opposite the 60-degree angle is √3, and the hypotenuse is 2. On the 45-45, opposite the smallest angle is 1. I call these my 2 unit special triangles, because most of the time when you see this referenced in books, they'll add an x. So this side is 1x, √3x, 2x. And that's because trig is all, well, the reason I don't add an x is because trig is all about ratios. Okay? Whether this is a 1, √3, 2 triangle or a 10, it just wouldn't matter if I wanted to make it 10 there, like that. The sine of 30 degrees is still 1/2. So when I go to look at all my trig functions, I don't care if it's a multiple. Let's erase that 10, and the sine of 30 degrees is 1/2. What's the cosine of 30 degrees?
√1.5.
Radical answers only. Remember what trig is all about. Trig is all about taking trig functions of angles and coming up with ratios, not decimals. I don't want you to do it in your calculator. I want you to do it by looking at this triangle. What's the cosine? Well, first of all, you got to know cosine is adjacent over hypotenuse. What's the adjacent side to 30 degrees?
√3.
So what's the cosine of 30 degrees?
√3/2.
Okay, good. What's the tangent of 45 degrees?
√3/3.
No?
Oh, 45 degrees, I'm sorry.
Right.
Did you say 45 degrees?
Uh-huh. What's tangent of 45 degrees?
Just 1.
Correct. Okay. So what I'm saying to you is that between these two triangles, you can figure out all 6 trig functions of these common angles, 30, 45, and 60. That's huge. when we get to the unit triangle, the most important part of the unit circle, is what I meant, is the first quadrant. Okay? In other words, every other quadrant, this is 1, this is 2, this is 3, this is 4. Every other quadrant angle can be reduced to a first quadrant. Okay? And I'm going to label these in degrees. At some point in trig, you're going to switch completely over to radians. But at this point, you probably are more comfortable in degrees. And in fact, there's nothing wrong with always taking radians, converting it to degrees, and then if necessary, convert it back to radians. As long as you know how to go from radians to degrees. Now, let me just say a couple of things about radians and degrees. If you have angles that are in radians, they usually have a pi in them.
Right.
And in fact, the conversion factor is 180 over pi or pi over 180, right?
Right.
Okay. Well, notice that pi over 2 is the same as 90 degrees. Pi over 3 is the same as 60 degrees. Pi over 4 is 45 degrees. Pi over 6 is 30 degrees. And notice what's common about all of those. The denominator times the degrees is 180.
Right.
So as long as you have just one pi in your numerator, this is a really nice, fast way of converting from radians to degrees. And by that, I mean, if you know pi over 3 is 60 degrees, well, what's 2 pi over 3?
120.
Yeah. And what's 4 pi over 3?
90.
No. Pi over 3 is 60. What's 4 pi over 3?
240.
Right. So if you can kind of memorize this system on the left here, where pi is the numerator only, then you can easily do problems where pi, has a coefficient in front of it.
Right.
Okay? And personally, I find this much quicker than applying the conversion factor. In other words, I could easily apply the conversion factor here to all of these. In other words, to figure out what pi over 2 is, I'm going to multiply it by, is it 180 over pi or pi over 180?
Pi over 180.
No, it's 180 over pi. And here's how you figure it out. If you're doing it this way,
it cancels out the pi.
It cancels out the radians. In other words, we're in radians, and we're trying to go to degrees. So you're going to have radians in the denominator of your conversion factor, because those will go away, pi's will cancel, and you'll end up with 90 degrees. Okay? So that's the traditional way of converting radians to degrees. My other way that I just showed you is just, I don't know, a little quicker. You don't have to figure out whether it's 180 over pi or pi over 180. After you work with it a while, you'll realize that, boy, if you can just memorize pi over 2, pi over 3, pi over 4, and pi over 6, it'll go a long ways towards converting stuff. Now, let's get back to the unit circle, because I was hesitant to even get into that conversion.
Okay. So one quick thing about that.
Mm-hmm.
Isn't that conversion the same as substituting pi for, or 180 for pi?
Yeah, that's why the conversion factor is pi per 180. Just like I would say 12 inches per 1 foot. Well, I could also say 1 foot per 12 inches.
That's just a ratio?
Yeah. In other words, that's correct as a conversion factor. It just depends on whether I'm starting with inches or feet. Well, this is correct if I'm starting with feet.
Right.
Well, this is correct if I'm starting with degrees. But this is correct if I'm starting with radians. Remember, you always are losing whatever units you're starting with, and you're trying to convert to the other. So just like, in other words, if I said to you, how many feet is 36 inches? Well, you're not going to use this one. That wouldn't work because that's 36 inches. Inches don't cancel.
Right.
I would use the one on the right. In other words, I would use this one here if I was converting inches to feet because my inches cancel and I'm left with feet. And that's always the key when you're working with conversion factors. Never forget that. The units are very important because it tells you whether to make it 1 over 12 or 12 over 1.
Right.
All right. Same with radians and degrees.
Okay.
All right. Let's get back to the unit circle here for a second. Now, these two triangles are going to allow me to figure out 30 degrees, 45 degrees, and 60 degrees. I will be able to figure out the sine, cosine, and tangent of those three angles, or of those three trig functions, for those three angles. Now, let's for a second talk about the other three trig functions. We have sine, we have cosine, and we have tangent. What kind of calculator do you have, William? Is it a TI-84 or an Inspire?
Inspire CX.
Okay. So you actually have all 6 trig functions on there.
Yes.
But if you had a TI-84, they only give you 3 trig keys on there, sine, cosine, and tangent, because the other 3 trig functions are reciprocals of these. Let's start with the tangent. What's the reciprocal of tangent?
Cotangent.
Yeah, that makes sense. That's why I started there. Now, there's only 2 others. There's secant and cosecant. So we have to figure out which one goes with sine, which one goes with cosine.
Cosecant goes with sine, correct?
Yeah, and notice the first letter of both is S and C, C and S. In other words, secant's never going to go with sine because I would have S and S. And that's the way I memorize it. And it's just a stupid little method. But when it comes to memorizing stuff, that's really what it comes down to, are stupid little methods. And in other words, I don't really, there's a saying with trig. You don't want to memorize trig, you want to know them. You don't memorize your name. When somebody says, what's your name, you don't have to access a place in your brain to figure out what it is. You know it, right? Well, I've read, is a great recommendation for trig. You want to know these functions so well that when I say, what's the sine of 60 degrees, you can tell me almost within 3 seconds. What's the sine of 60 degrees?
Root 3 over 2.
What's the cosecant of 60 degrees?
Cosecant.
It's the reciprocal of the sine. In other words, Yeah, 2 over root 3. And let's talk about rationalizing the denominator.
Yeah.
I've spent 8 years tutoring trig and have dealt with this rationalizing the denominator process. Well, that can be a little counterproductive because sine was root 3 over 2, cosecant was 2 over root 3. And I had a student tell me that his trig teacher told him, do not rationalize the denominators, which is an excellent piece of advice if your teacher will go for it. Now, some teachers will, some won't. And here's why he said that. What is the sine of 45 degrees?
1 over root 2.
Okay, and I could spend a lot of time rationalizing that. Becomes root 2 over 2, right? But now what if I say, what's the cosecant of 45 degrees? And I'm starting with the rationalized version. Well, what's the cosecant? If I look at that, I got to flip it, so it's 2 over root 2. And now I got to rationalize that again.
Right.
Well, it would have been easier had I not rationalized the first one. Let's just leave the first one as 1 over root 2. And now the cosecant is what?
Just root 2.
Yeah. In other words, we saved ourselves a lot of trouble by not rationalizing the first one.
Okay.
And in all honesty, if you put 1 over root 2 into your calculator, you'll get exactly the same number to as many decimal places as you want as root 2 over 2. They're the same number. It's just kind of a convention in math that how do you divide by an irrational number? It doesn't make sense in a way. But with trig, because we're so often dealing with the reciprocal, this teacher decided to throw that rule out the window, and I love it. I don't think you need to rationalize it. There is nothing wrong with the answer 1 over root 2. Now, do we need to turn it into a decimal? Almost never.
Okay.
You always want to give your answers in ratio and radical format, not decimals. Root 2 might be 1.4 and change, but I'm never going to write it like that. I'm going to write it root 2 always.
Okay.
Okay? All right. So, now, between these two triangles and what I've written on the left, you can figure out all 6 trig functions of 30, 45, and 60, correct?
Correct.
Okay. Now let's talk about, we're going to hold the quadrangles. Quadrangles are multiples of 90. In other words, 90, 180, 270, 360. Those are called quadrangles. Quadrangles. Q-U-A-D. Okay? And I'm going to hold off on those for just a second. What I want to show you how to do is to take all angles that are not in the first quadrant. Let's take the angle 150 degrees. Okay? The secret to taking trig functions of angles greater than 90 are really to convert them to their equivalent first quadrant angle.
Right.
Well, what that turns out to be, they have a term called reference angles. Okay? The reference angle is the angle that is made with the x-axis, the acute angle. Well, what is alpha right there? If the angle I'm talking about is 150 degrees, what reference angle does it make?
30.
Yeah. And guess what? the trig functions are all the same as they are for 30 with a different plus or minus sign. That's the only difference. So if I said to you, what is the sine of 150? Well, the equivalent reference angle is supplementary to that, so it'd be 30, so it'd be 1/2. So the sine of 150 is 1/2. And is all I have to do is figure out whether it's positive or negative. Well, there's other things. Here, let me finish drawing my unit circle so you know what I'm talking about here. And again, everything I'm putting on here, you want to memorize. If I want to convert second quadrant angles to their equivalent reference angles, I do 180 minus theta. Notice that when theta was 150, that turns into 30. If I'm in the third quadrant, I do theta minus 180, and if I'm in the fourth quadrant, I do 360 minus theta. Okay? That's huge. That information right there. I'm going to add one other thing. All students take calculus. Have you heard that expression?
No.
You will. Okay, and here's what it means. It means that in the first quadrant, all 6 trig functions are positive. In the second quadrant, only the sine and its reciprocal cosecant are positive. Everything else is negative. In the third quadrant, only tangent is positive, and of course it's reciprocal. If tangent's positive, cotangent has to be positive. Reciprocals always have the same plus or minus sign as their reciprocal. And the C means that only cosine and its reciprocal are positive in the fourth quadrant. So for a moment, let me erase the circle even. Now, what you're looking at on this page is going to allow you to figure out the trig function of any angle that is a multiple of 30, 45, or 60. Remember when I originally said, what's the sine of 225?
Right.
What quadrant's that in?
3.
What's its equivalent first quadrant angle? Based on this theta minus 180.
45.
And that's the way I kind of like to write it, like that. Now, what's the sine of 45 based on the triangle?
No, 1/√2.
And what is its plus or minus sign? Is it going to be positive or negative in the third quadrant?
Negative.
And that's the way I do all of them.
Okay.
And that information alone is all you need to do the entire unit circle that they expect you to memorize. I'm sure by now you've seen something that looks a little like this. And it's split up into 16 slices. And they expect you to memorize all 6 trig functions at all 16 slices. Well, that's 6 times 16, that's 96 things. And they want you to memorize 96 things. Okay, where this angle is 30, this one's 45, and so forth and so on. And they actually give you, or will give you, a picture of the unit circle and say memorize every point on this thing. And some people would go about doing it this way. Well, this is a ridiculous way to memorize the unit circle.
My teacher made us fill one out. That's what I've been using.
It's crazy. If I gave you a 16-digit credit card number to memorize, are you going to memorize it as 16 numbers? No. You're going to break it into groups of 4. You're going to memorize the first 4, and then the second 4, and the third 4, and the fourth group. And that's the way that it's easiest to memorize anything, is in small groups. They have proven repeatedly that humans don't memorize things greater than 7 very well. And that was the original theory about why phone numbers were 7 digits, because people could memorize 7 digits. If I give you 8 digits, not so easy to memorize. And that's just kind of a fact about humans. And so I don't want anybody to memorize 16 things. But notice, if we go back to everything on this page, this allows you to figure out all 16 slices. Almost, not quite. You still can't do the quadrangles. But you can do 30, 45, 60, 120, 135, 150, 210, so forth and so on, based strictly on everything that you see on this page right now. You don't need any other information to do the unit circle.
Right.
Now,
and the coordinates for the axes, it's just 1 for 0 pi, 1 comma 0, and then 0 comma 1, negative 1 comma 0.
Well, let's talk about that. Let's talk about that. I don't want to ignore that. Okay? Let's take a 45-degree angle. Let's take a 30-degree angle. I prefer it. Now, it's called a unit circle. Believe it or not, the unit circle is your first exposure to polar coordinates. They don't say that, but that's what it is. Okay? And no matter which quadrant I'm in, the hypotenuse is 1. And it's always a positive 1. That's the nature of polar coordinates. Is no matter how you wrote it, the only 2 things that matter with polar coordinates are the length of this line and this angle. That's it. Okay? So, if that's a 30-degree angle and the hypotenuse is 1, well, let me create a triangle here. And that's x. What's cosine of 30 degrees? Based on my triangle.
Just x.
Yeah. What's the sine of 30 degrees?
Y.
Okay. Now, that's critical. That means that every single spot on our unit triangle, or our unit circle rather, the x-coordinate at the end of that ray is the cosine, and the y-coordinate is the sine. So I'm going to write everything. In other words, my coordinates of that point are cosine theta, sine theta. And when they want you to measure the unit circle or memorize the unit circle, they usually want it in this format. In other words, they want to know the x and y coordinates of each spot on the unit circle of the 16 spots. Correct? Okay. So this point would actually be root 3 over 2. That's the cosine of 30 degrees. Sine of 30 degrees is 1/2. So they want you to memorize that this spot on the 30-degree ray is square root of 3 over 2 comma 1/2. But the real way you should memorize it is to know that the x-coordinate is cosine of theta, the y-coordinate is sine of theta. That's all you have to know. And now you can actually fill out the unit circle perfectly. And here let me show you how to do the quadrangles. Quadrangles work really nice based on this model. If I draw a 0-degree angle, what's the coordinates on that point right there? It's the x.
1, 0.
Yeah. Well, if the 1 is the cosine of theta, then what's the cosine of 0 degrees?
1.
What's the sine of 0 degrees?
0.
Okay. Now let's go up and look at the 90-degree angle. What's the coordinates of that spot?
0, 1.
What's the cosine of 90 degrees?
0.
The sine of 90 degrees?
1.
Okay. Now we'll go over and look at the 180-degree angle, the coordinates of this spot.
Negative 1, 0.
What's the cosine of 180 degrees?
Negative 1.
Good. And the sine is clearly 0. And finally, let's look at a 270-degree angle. Coordinates of that are 0, minus 1. Therefore, the cosine of 270 degrees is
0.
And the sine of 270 degrees?
Negative 1.
Now you're complete. In other words, now, without a calculator, you can do every single multiple of 30 or 45 degrees, including angles greater than 360. In other words, if I said, what's the sine of 390? Well, you would find the coterminal angle. In other words, that's 30 degrees beyond 1 unit circle. So that's exactly the same as the sine of 30.
Right.
So now, if you could memorize everything on this page, you could do all of that. You could draw the unit circle and draw the x and the y coordinate at the end of each ray. Not only that, but by knowing the coordinates of 0, 90, 180, and 270, you also know all your quadrangles without memorizing the curve. Now, if I were you, I would take a quick picture of this page.
Okay.
With your camera, with your cell phone. Because you want to memorize every single thing that's on it. And you're 100% there for doing your unit circle if you can recreate this page from scratch, just like I did. I wasn't referring to any notes or anything. I've done this so much that I've got this thing memorized in my sleep. But there's nothing on here that doesn't need to be memorized. You need to memorize the all students take calculus.
Yeah, that's helpful.
Notice that all these angles are measured counterclockwise. Plus angles are counterclockwise, minus angles are clockwise. So if I'm talking about a negative 30-degree angle, I'm talking about that one right there. It is the same as 330, but I don't need to necessarily use that information. There's other trig identities where it's actually going to be easier to know that the sine of minus 30 is the same as minus the sine of 30. Because we all know what the sine of 30 is. It's 1 over 2. So the sine of minus 30 would be minus 1 over 2. And that is the same as the sine of 330 degrees, but it's a little quicker to get there by using the negative angle than it is to convert it to a positive angle. Although, at this point, You don't lose anything by doing them all by converting them to positive angles. That's perfectly fine.
Right.
But you will reach a point where you will realize that you're doing 2 unnecessary steps by converting it to a positive angle instead of using its odd and even properties. Now, what do I mean by odd and even, as long as we're talking about it? Sine and tangent are both odd. If you remember, odd functions have this property. The sine of negative x is the same as minus the sine of x. And the tangent of negative x is the same as minus tangent x. Cosine.
Is that the same as inverse, or is inverse?
No, it's not. Odd and even are unique. Okay. Inverse is completely different. I'll get to that in a second if we have time.
Okay.
But the cosine of a negative angle, well, that's the same as the cosine of the positive angle. So if I said, what's the cosine of minus 60 degrees? Well, it's all I need to do. I don't need to go through and convert it to a 300-degree angle and then go through that conversion to figure out what its equivalent first quadrant is. I can just say that the cosine of minus 60 is the same as the cosine of 60. Well, I know the cosine of 60 is 1/2. So I can do it in 1 step as opposed to doing it in 3 steps if I have to first take that negative angle and convert it to the equivalent positive angle.
And is that because the 1/2, it's on, for 60 degrees and negative 60 degrees, those are both to the right of the y-axis?
Well, let's look at our triangle. Always refer to these triangles. This is where you get your basic first quadrant answers. In other words, you don't really have to memorize anything. All you have to do is memorize the 3 dimensions of that triangle and the 3 dimensions of this triangle. And SOHCAHTOA. Notice that SOHCAHTOA is memorizing 3 things. This triangle on the left is memorizing 3 things. This triangle on the right is memorizing 3 things. This reciprocal relationships or identities is memorizing 3 things. If I look over here at my unit circle, I'm memorizing 180 minus theta, theta minus 180, 360 minus theta. That's 3 things. And all students take calculus is 4 things. So whenever somebody says to me, what is the trig function of some big angle, I only have to access groups of things that I've memorized that are 3 or 4 in number. That's it. Let's do one more example here. Let me test you a little bit. What is the tangent of 225? And I put parentheses because that to me is a clever little way of, well, let's figure out what the tangent of its equivalent first quadrant angle is. Well, what's the first quadrant angle?
45.
What's the tangent of 45?
1.
And what's the plus or minus sign?
Positive.
That's the way you do it, in steps. In other words, I took it, I figured out that, step 1, I figured out that, step 2, and I figured out that, step 3.
Okay.
Okay? And I guarantee you that will work really well for you. You just have to make sure you have everything on this page memorized. And you can figure out any trig function, all 6 of them, based on that. Now, to do the unit circle the way they want you to, in other words, to be able to give them that answer there at the end of the 30-degree ray, you also have to remember that the x-coordinate is cosine of theta and the y-coordinate is sine of theta. So as long as you can figure out cosine of theta and sine of theta, you're fine. Okay, you don't even need to figure out tangent of theta for any of these things. Although you want to be able to figure out tangent of theta, but in order to do the official unit circle, the x-coordinate is cosine theta, the y-coordinate is sine theta. That's all you have to know.
So isn't tangent just sine theta over cosine theta?
Yes, it is. So if I wanted to know the tangent of 30 degrees, I could take 1/2 and divide it by square root of 3 over 2. But to me, that's actually harder than looking at the triangle. What's the tangent of 30 degrees?
Root 3 over 2.
No.
No, sorry. 1 over root 3.
Right. And for now, leave it like that. If you end up with a teacher that says, rationalize everything, never give me an answer that's got an irrational denominator, well, then you're going to have to rationalize this stuff. But the best thing I ever heard from any teacher in 8 years was this one just recently that told all of his students, do not rationalize your ratios. Okay, now let's talk about what you said inverse.
Right.
If the sine of 30 degrees equals 1/2, then the inverse sine of 1/2 equals 30 degrees. These two are if and only if. If one's true, the other is true. Okay? And here's the thing to remember. We take trig functions of angles to come up with ratios. We take inverse trig functions of ratios to come up with angles.
Oh, right, we did that in physics. Okay.
Okay, now let's look at a triangle that you're also very familiar with. Been dealing with this triangle for 3 years also. Right? It's the lowest perfect Pythagorean triangle. Well, notice that the one thing you don't know about this triangle is what is this angle right there? Correct?
Right.
It's not like our two special triangles. If we look at our two special triangles, they're based on the fact that that's 30 and that's 60 and 90. And this one's 45, 45, and 90. But this 3, 4, 5 triangle, we certainly know that this is a 90-degree angle. How would I figure out what theta is?
You take the ratio of
You would take
3 over 5.
Exactly.
That's the inverse sine of 3/5.
Exactly.
Theta.
Exactly. Okay. That's what inverse functions do with trig. Is you use trig functions to find ratios, you use inverse trig functions to find angles. Turns out that that angle is about 37 degrees. It's actually 36.9 something or something close to 37. Okay?
36.8699.
Yeah, and you can get that out of your calculator. And but that's a use for, you're going to encounter all kinds of problems where they give you triangles and they give you the dimensions of the triangle and they want you to find the angles. Okay, well, how we find angles is by using inverse trig functions.
Okay.
Now,
that's really cool.
They're going to confuse you a little bit because the relationship between degrees and radians is a little strange. It's not probably what you're thinking it is. If I compared it to the relationship between feet and inches, but really, if you were talking about feet and meters, okay? Those are both linear measurements. I can give you the exact number of meters per foot. and that is a perfect relationship. Well, not quite the same between degrees and radians. Radians turn out to actually be a number. Pi over 2 is a number because pi is 3.14, right? So if I do pi over 2, I get 1.57 and change. And the reason that you end up using radians almost exclusively has to do with calculus. Calculus, there's a huge part of trig in calculus. And unfortunately, when you take the derivative or the integral of trig functions, it only works if they're in radians. So to do all calculus involving trig functions, which is a large deal of it, you have to be in radians. And radians are actually numbers. They're not technically angles.
Right.
And that's confusing, especially when I'm trying to teach people what the difference between a trig function and an inverse trig function is. Because to me, this analogy here is the perfect one. We take trig functions of angles to get ratios. We take inverse trig functions of ratios to get angles. Well, the moment I start writing that 30 degrees as pi over 6, which I could do, now I'm really taking a trig function of a number to get a ratio. And likewise, if I'm taking the inverse trig function or the inverse sine of 1/2, and I want the answer in radians, that's pi over 6. So again, I'm taking the inverse trig function of a number to get a number. So when actually the explanation works a lot better if you leave it in degrees. But just know that's the basic understanding of trig is you take angles to get ratios and you take inverse of the ratio to get the angle. And don't worry about the fact that radians are actually a number. And the explanation for that is an extremely complicated one. It might take me an hour to explain to you why that's true.
Okay.
Why is 1 radian equal to the radius of that circle? And why radians are actually numbers and not angles.
Okay.
So for now, just kind of take my word for it. And your teacher's word, because I'm sure they have as much difficulty explaining that relationship as I would. So in a way, work with angles until you get more familiar with converting to radians, and then understand that while radians are a number, they're also an angle.
Okay.
Okay? That's the easiest way to deal with it. Now, let's go back. Okay, so everything on this page that you took a picture of allows you to do any positive angle, right? As long as it's a multiple. And here's the thing. They're never going to ask you what the sine of 29 degrees is.
Okay, I was about to ask, is that not a...
That's not something that you ever are going to need to know, and it's only something you can get out of a calculator or a table. Okay? When I went to high school, we had tables in the back of our math books that gave you every trig function for every angle from 0 to 360. So if you wanted to look up the sine of 29 degrees, you looked it up. Seriously, same as what you would do now, you'd put it in a calculator to come up with it. The only ones that they are going to insist that you memorize are these really common ones. And by common, I mean multiples of 30, 45, or 60. Actually 30 or 45. 60 is a multiple of 30. Yeah, multiples of 30 and 45. And that will cover all your quadrangles, And the way to memorize the quadrangles really easily is this little technique I used here, where you figure out what the coordinates are, and knowing that the x-coordinate is cosine and the y-coordinate is sine. Okay. So let me think what else I cover. This is a fairly standard tutoring session for me for first year trig students who are just entering the unit circle phase. I give almost the same exact tutoring session to every single trig student. I should just record it and play the recording, and it wouldn't be much different, other than the fact that, you know, I need to ask you questions along the way, like what was the sine of 225 degrees, to make sure you're understanding it. But other than that, this is what I give to everybody. Now, let's talk about if things are in radians for just a second. If things are in radians, then instead of 90 degrees, that's pi over 2. And instead of 180, that's pi. And instead of 270, that's 3 pi over 2. So you might see unit circles labeled in radians, and you probably will very quickly. They tend to switch you to radians very rapidly. Okay. Now, this 180 minus theta becomes pi minus theta, if everything's in radians. This theta minus 180 becomes theta minus pi, and the 360 minus theta becomes 2 pi minus theta. So if I gave you what's the sine of 3 pi over 4, you don't really need to convert that to degrees. You can use pi minus theta. Well, if theta is 3 pi over 4, then pi minus theta is pi over 4, right? So the equivalent angle is pi over 4. Well, once you learn radians well, you'll know that's a 45-degree angle. And so the sine is 1 over root 2. And it's in the second quadrant, so it's plus 1 over root 2. And I did the whole problem without converting from radians to degrees. And you kind of want to get to that point as quickly as you can, because otherwise it's just an unnecessary step to have to convert that to degrees and then do everything in degrees. Okay? Not that you need to do that immediately. I wouldn't even say you need to memorize it immediately. But you maybe want to memorize this 180 minus theta is also the same as pi minus theta, if I'm dealing in radians and not degrees. Because they're going to ask you, you know, what's the tangent of 7 pi over 6? And you can go through the conversion, or you can realize that's the same as the tangent of pi over 6, with the same plus or minus sign. Okay. So again, maybe you want to take a picture of this page also, because this page has the radians in addition to the degrees. Even though you could make that conversion yourself. In other words, since you know that pi is the same as 180, well then 90's got to be pi over 2, 180's got to be pi, and 270's got to be 3 pi over 2.
So one quick question. In your opinion, is it easier to think of it as 3 pi over 2 or 3 halves pi for 270 degrees?
Well, most people verbally would always call that 3 pi over 2. And that's all of these angles, like 225, 210, are usually in terms, I would always call that, I wouldn't call it 7/6 pi, I would call it 7 pi over 6. Why that is, I'm not sure. It's just convention. In other words, it's the same thing as 7/6 pi. But you never convert that to a number. So typically with algebra, I would say 7/6x. I would not say 7x over 6, even though they're the same thing. But in algebra, I'm going to multiply 7/6 by whatever x is. Whereas with trig, you're not going to do that. You're going to leave it as 7 pi over 6. You might convert it to degrees, but you're not ever going to multiply 7/6 times pi. I mean, I shouldn't say never. There are geometry problems where you're trying to measure the height of a mountain or something, and yeah, eventually you have to convert this pi to a number. But most of the time you leave it in terms of pi. In other words, because we don't ever multiply that, we call it 7 pi over 6 rather than 7/6 pi. Okay. Terminal, coterminal angles, you're good there? Those are pretty easy. They'll give you questions like they'll give you an angle and they say, give me one coterminal positive angle and give me one coterminal negative angle. So if I gave you the angle minus 30 degrees, give me a positive and a negative coterminal angle. What's a positive?
330 degrees.
That's a positive one. What is a negative one?
Negative 390 degrees.
Yeah. So coterminal angles are a piece of cake, really. Just multiples of 360 or else multiples of 2 pi if you're in radians.
Right.
That's probably a good place to stop for this session. I've loaded your brain up with tons of information here, and the only thing I can say to you is try to memorize everything you see on this page, such that given a blank page you could recreate it. Because if you can recreate it, then you can do the unit circle. And it's easier to memorize it this way than it is to memorize 16 slices times, to memorize 96 things. Right. It's better to be able to figure out those 96 things rather than to memorize them.
Yeah, right. Well, thank you very much, Mr. Callan.
Okay, William. And I know you've got another few sessions scheduled. We'll do whatever you're working on at that point in time. Try to bring problems to the sessions. I don't need it on this session. This is kind of my standard unit circle session, but from here forward, it's better if you bring me problems that your teacher has given you. Okay?
Well, thank you very much, Mr.
All right. Talk to you next time. Bye-bye.
Bye.